everyone. In this video, we will be discussing some basic thermodynamic terms before studying our statistical mechanics in our MSc Physics course. So let us go to the basic thermodynamic terms. So let us first try to define thermodynamics. Again, it's a very lower class definition that thermodynamics is the study of relationship between heat, work, temperature and energy. Here actually all of them are synonyms of each other because heat and energy are same. Again, heat is also related to temperature. So here they are all related to each other. So their dynamics, as we say, thermos is heat and again dynamics is power, energy. Their dynamics is the study of thermodynamics. So in broad terms, thermodynamics is the study of energy from one place to another or from one form to another. How a energy transfer takes place. In very broad layman terms, we will say define thermodynamics in this way. Then we will improve our definition further. Now, whenever you learn about thermodynamics, there are some things which comes to our mind. One is the system, one is the boundary, and one is the surroundings. So now, what is a system? System is any region in space which is separated by a flat surface which is known as a boundary. So the boundary is the one which is separating or isolating the system. And from what it is isolating? The boundary is isolating the system from the surroundings. So let us once again define a system. System is the region enclosed inside a boundary which is the subject of study, where we apply all our laws. And what is the boundary? Boundary is the closed surface, which is actually differentiating between the system and the surroundings. As we know, boundary is very important. Even in our electrodynamics, we talk about the boundary conditions because all changes happen when you cross the boundary. All changes happen when you cross the boundary. Now here, the environment outside the boundary is known as the surroundings. Okay, surrounding is the neighborhood of the system where which it interacts. Now again, systems can be of two types: closed systems where you are having no exchange of energy or matter with the system, and there is no exchange of energy or matter with the surroundings; and open system where there is exchange of both energy and matter, or energy and particles. So now we have defined the prerequisite for a thermodynamic course, that is a system, a boundary and a surrounding. Now let us try to define in our daily life. Suppose you are having a container having some water, a hot water let us say, then it is a open system because the heat is being continuously exchanged with the surroundings. Surroundings is the environment. Suppose you are keeping that hot water inside a thermos flask. You are trying to what? You are trying to isolate the system a bit so that the hot water remains there for some more period. So that is the very common layman example of an open and a closed system. Now here, whenever we learn about thermodynamics, we come across two point of view. What is the macroscopic point of view and microscopic point of view? So whatever thermodynamics which we learn in our lower classes, we always discuss in terms of macroscopic point of view. That is variables or characteristics around the range of human scale or larger. Things which we can measure through our eyes. And what is the microscopic point of view? The microscopic point of view, it deals with molecular scale or smaller scale. So here this is a very standard definition. Actually, the physical impact is much larger. So now we will discuss what do we mean by a microscopic point of view. It's not just that it is on a microscopic scale, but again microscopic point means actually we are involving a lot of things. That is a system having n particles existing in epsilon 1 up to epsilon n states. They interact with each other, and most important thing, that is we go with the mathematics of probability. Till now, whatever mechanics we were dealing with deterministic mechanics. So we were using the classical things when the we were talking about deterministic things. Now we will talk about the mathematics of probability. That is, the equilibrium state will be the most probable state. And again, we will be using the molecular distribution to find out the most probable speed. We get the average speed, we get VRMS. So, here we have gone from a deterministic level to a probabilistic level in microscopic view, because the number of particles, the number of particles constitute the system is very large to individually distinguish and determine. So let us say, now with that we will go to another thing. This is something which we will be discussing later on also, because at a very lower scales, what happens is that the de Broglie wavelengths tend to overlap, making the molecules indistinguishable. Generally happens at very low temperatures. So this part, for the time being, we'll take it as it is, and we will discuss further in our further classes of statistical mechanics. Now here comes the microscopic versus macroscopic. Now, is microscopic and macroscopic both actually opposite to each other? No. Whenever we are defining two things, one is in microscopic scale, another is in a larger scale, doesn't mean they are totally opposite to each other. They are not incompatible. Microscopic behavior is actually used to predict macroscopic behavior. So they are not incompatible, they are related. That is, whenever you are discussing about a pressure in a container, it is about the molecules of the gas hitting the walls of the container and exerting the force. So there, microscopic behavior is actually determining the macroscopic parameter. But as such, thermodynamics, which we learn in our lower classes, is purely macroscopic in nature. And that's what we are trying to make it change. We try to justify, or we try to predict macroscopic behavior via microscopic viewpoint in our statistical mechanics course. Now, with that, we will move further and talk about an important thermodynamic thing, that is the thermodynamic equilibrium. So here, thermodynamic equilibrium means a system should have thermal, mechanical and chemical equilibrium. Thermal equilibrium is known to you is there is no exchange of heat. Both the systems do not exchange heat. Mechanical equilibrium, the net external force is zero. That means in that case P is a constant. And in chemical equilibrium, what happens is that there is no chemical reaction. The concentration is remaining constant. The chemical potential is a constant. So in such cases, you will call it as a chemical equilibrium. So thermodynamic equilibrium, a system is said to be in thermodynamic equilibrium when it is in a state when there is having no exchange of matter or energy, because all these three things will constitute that. So there is actually no exchange of energy or matter with the surrounding. So attains a state of, then only it attains a state of thermodynamic equilibrium, or in other words, there is no spontaneous change in any macroscopic property. So there is no spontaneous change in macroscopic property. Then you call that system to be in thermodynamic equilibrium. Now, once again try to define thermodynamics is the science of energy transfers and its effect on the physical properties of substances, systems. An equilibrium state is the one in which the properties of the system do not change with time. So again, once again, we have tried to define the equilibrium state of a system. Now, we will discuss some important characteristics. Let us say extensive properties and intensive properties. Let us say take A, let us take B of a thermodynamic system. It's proportional to the amount of matter present, independent of the amount of matter present. Common example volume, this is pressure, temperature, etc. Now here we will discuss another thing which is known as thermodynamic limit. So when n tends, number of particles is very large, when V is very large, n by V is equal to fixed. In the beginning we have said P is intensive, V is extensive, T is intensive. Now whenever we define certain things, we try to put every quantities as intensive. For that reason, instead of using V, we can use small v, which is the specific volume, which is V by N, which we know is fixed. So it will behave like an intensive property. Similarly, the density N can be N by V, which is again fixed, which will behave like a intensive property. Now once we are done with the intensive and extensive properties, let us try to define the equation of state. So actually you have all the thermodynamic quantities, and that function which is connecting all of them is equal to F PVT is equal to 0. So such a expression is known as the equation of state. So these variables are not independent of each other, they are related to each other. A common example is our gas law, PV is equal to nRT, and all those things, they constitute the equation of state, where F is the function of the characteristic of the substance. Now, any change in the external conditions will change the equilibrium state of a system, and such a case is known as a thermodynamic transformation. So any change in the external conditions will change the equilibrium state of a system. Suppose let us consider you are having a container, you are having a piston. So you have put inside some gas inside it. This is a movable piston. So it had attained equilibrium. Then you what will happen? You lift the piston a bit. So again what happens? The volume changes. So naturally what will happen? The pressure will also change. So there is a change in the equilibrium state of the system. Such a transformation is known as a thermodynamic transformation. Again, these transformations can be of two types. You can suddenly release the piston, or you can release the piston slowly. So let us see how does that happens. If the transformation is very slow, system remains in equilibrium throughout. Such a transformation is known as quasi-static transformations, and such transformations are reversible. However, if you make a sudden change in external condition leading to a drastic change, such a transformation is known as irreversible transformation. Now here, let us see, when we try to draw both the reversible and irreversible transformation, let us say this is stage 2, this is state 1. If it goes directly passing through some non-equilibrium states, you will call it what? You will call it as a irreversible transformation. If it is passes through slowly, if it goes from 1 to 2, and each state is an equilibrium state, then such a transformation is a reversible transformation. Again, I have drawn PV because generally for any thermodynamic processes, the standard curves which we draw is PV, and sometimes we draw TS curves. For a Carnot cycle, we also draw TS curve, and this is the PV curve for a Carnot cycle. So PV is the standard coordinates which we draw. So therefore, I have expressed it. Even the work done, PDV is also drawn using PV curve. Here, one thing, once again, let me tell you, small equilibrium states, it is passing from one point to another. So the change here is not spontaneous. Whereas an irreversible process, the change is spontaneous. It happens all of a sudden. Generally, natural processes are spontaneous in nature. Otherwise, you have to move the system very slowly, such that you reach from one point to another, and the steps taken are very small. A small change in temperature, very gradual changes. That leads to quasi-static transformations. Now we will again go what is the work done over an infinitesimal path. Again, this is the standard thermodynamic expression, that is dW is equal to PdV, and the path is A to B. So it will be PdV A to B. Now some standard thermodynamic let us say conditions, let us say when you are having a some change is taking place where T is equal to constant, you will call it as an isothermal case. When P is equal to constant, is an isobaric case. P is equal to constant, isobaric case. Suppose the heat involved is 0, that is the system is not taking any heat from the surroundings, you are not supplying any heat. Such a system is known as a adiabatic process. Now we will quickly refresh our zeroth law. I will not be writing the statement, that you will write. Is that suppose you are having two systems A and B, which are separately in equilibrium with system C. A, B separately in equilibrium. Separately in equilibrium with C. Which means what? A and B in equilibrium with each other. Thermal equilibrium with each other. That is the basic, very basic definition of zeroth law. Zeroth law tries to define equilibrium. Now we will go with the first law of thermodynamics. First law, I have not directly written the first law. It is when you apply heat, what happens? The heat applied to a system goes to change in internal energy plus work done. So I have written internal energy del U is equal to del Q minus d del W, where del W is PdV. Now here, instead of change, I will write du. Because this is an exact differential. This, though I have written dq and dw, they are actually not exact differentials. Many books represent them as del q minus del w. Why? Because this is an exact differential which depends only on the endpoints. Work done and heat, both, or energy supplied, both are path functions. So they are not exact differentials. They are inexact differentials. Now let me tell you what is an inexact differential. Inexact differential is, suppose you are having a function xy such that dou f by dou x dx plus dou f by dou y dy. Let us name this as p. Let's name this as q. So dou p by dou y, that is dou square f by dou y dou x, should be same as dou square f by dou x dou y. That means if you differentiate first with x and then differentiate with y, should be same as if you differentiate first with y and second with z. It holds good for point functions. That is the functions or conservative forces which depend on the endpoints, but not for path functions. So here, internal energy is an exact differential, whereas these, because it is not a path function, it depends on the endpoints, whereas these two are path functions. So again, we will wind up by saying for a magnetic system, we can write the first law of thermodynamics as du is equal to dq. Instead of p dv, we will write it as h dm, where h is the external magnetic field and m is the magnetization happening due to it. So in this class, we have tried to define some thermodynamic parameters, intensive and extensive quantities. What is the microscopic and macroscopic view? Are they compatible? Yes, they are compatible, because we are using microscopic view to explain macroscopic phenomena. So they are compatible. Then we have discussed transformation, which is very important. That is a slow varying transformation, which is generally reversible, and a drastic transformation, which is the irreversible transformation in a equilibrium state. So that's it. Thank you.